We're starting now. So we're live now. All right, so welcome everybody to the last day of our summer school and symposium. Today we will have last of the 3 lecture series by Kilian and Andrew. We'll start with Kilian's lecture. And I think the plan is to take us to useful tools that are really used everywhere today, like CNN and so on, and also connect to the tools that we use in our recent publications. So with that, Kilian, please take us away.
Okay, hello, can you hear me? One second, let me share my screen. Okay, good. Today's last day, right? Nice to see still so many people here. This is exciting. One sec. Okay, can you see my? Yeah, you can see it, right?
Yeah.
Okay, good. First, I have to say sorry. I had a plan of showing you starting with a bunch of demos, but my son actually just got sick this morning, so I had to change my plans. But I can do a quick recap of what we did last time. So we've been talking about actually, and I need to see. So 1 second. I need to see the participants. Okay, here we go. All right, good stuff. So last time we talked about neural networks, and essentially what I told you is, well, neural networks are really, really simple, right? So we have we have some data, and well, beforehand, maybe we had something. Sorry, 1 sec, my screen is not set up properly. Okay, good. Like what if our data is nonlinear, right? And so we, beforehand we would have just had a single line or something, but in this case, linear regression or something doesn't cut it, right? We need something nonlinear. And one approach is to kind of come up with clever features that basically where in some higher dimensional space, a line, a single direction would actually correspond to such a curve. But neural networks actually do something slightly different. They basically say, well, we just have many little functions that we kind of combine, right? Basically add up many piecewise linear functions. And this way we can approximate anything. Any arbitrary continuous function can be approximated with enough piecewise linear functions arbitrarily well. And the idea is very simple, that basically we learn a lot of functions that basically have the following format that are kind of like just like this, right? So they basically have a little hinge here. These are called this is what happens when you have a linear function, then you have a rectified linear unit. And so, they look like this or like this and so on. You have many, many such little guys, and you add them up. And when you add them up, let's say, for example, I would add up these functions here, right? What would I get? I would get here, and then I go up, right? And then when I add this component down here to this, right, then I'm actually getting something that maybe is, well, maybe slightly negative, and then I'm adding this guy, so now I'm going becoming positive again. And so this is essentially what you end up having, right? And so you can see how basically having many piecewise linear functions, you can approximate anything. And the way this works is initially you just initialize them randomly. So you just have a bunch of some function like this, and then with gradient descent, you just slowly move these kinks around to actually fit your data. Any questions right now? Are people happy? People give me a thumbs up if they still remember this. Okay, good. So, well, in terms of what algorithms are useful, well, actually, those algorithms are already very useful. So people use neural networks everywhere, right? this specific kind of neural network is called a multi-layer perceptron. And it's funny, it really is exactly what was invented in 1964, right? So it really hasn't changed a whole lot, right? What has changed is computers have gotten a lot faster. So in 1964, when Frank Rosenblatt invented it, he had his own custom-built hardware and it filled the entire room, right? And nowadays you can just, run this on your phone, right? Like, and then it can be 1,000,000 times larger. And so that's essentially one of the big factors that has recently led to the big popularity of neural networks, is that we have these vector units, these graphical GPUs that are really, really fast, that allow us to train them very fast. Okay, so just to why are they called networks? Well, because people kind of draw them like this. So you have your input X, and you basically say, well, my first linear function is basically, and this is my first, we call this the hidden layer. This here is my first linear function, and it's an input, takes every single dimension of X as an input. Then the second linear function takes every single dimension of X as an input, and so on. And then let's say the output here takes is again a linear function, right? But it takes as input the outputs of these linear functions. So basically, I'm learning these linear functions, and then I'm sticking them into another linear function. We can also call them hierarchical representations. The story actually is kind of interesting. Neural networks were all the rage. Like, when Frank Rosenblatt invented the perceptron, everybody talked about it, right? The whole world talked about it, because the idea was we have this artificial neuron. It's going to be a really, really big deal. It's going to change everything. Then people became very disillusioned because, I guess, computers weren't fast enough. Quick question. So just to clarify again, should I go the first input layer as a matrix? Oh, okay. Think of the first as a matrix. Actually, let me just clarify this. Here, H of X, each one of these is just a W transpose X plus B. Each one of these guys will be W1 and B1. And this here down here is WM transpose X plus BM. And if I take all these vectors, W1, W2, Wm, I can just shove them all in one massive matrix, W1, Wm. And so then I can actually write this entire transformation going from the input to, going from this vector to this vector, where this vector here, the second vector is this essentially basically F1 of X, F2 of X, Fm of X, right? Is actually, we can just do this in one matrix operation. Like this here is X, and this here is Wx plus B, where B is a vector, and I apply a transition function. This here is a rectified linear unit. So rectified linear unit is just max Z with 0. Does that make sense? So the neural network is acting on a single data input. So this is just when you take one input in, this is what happens. And during training, you push in many, many inputs. For each input, you get a prediction, you get a loss, and then you take the gradient to kind of make this, to change the weights to make these predictions better. Does that make sense? So at the end, basically, this xi is the input, this is h of xi is the output. And then you have a loss function that basically, some loss of, h is basically a sum over I equals 1 to n. And you have, for example, you could have the following, h of xi minus yi squared. And this is basically now a squared. So you have this label. For each I, you basically say, this is what the prediction that I want. This is the prediction that I'm getting. I'm minimizing the square difference. And in order to change my neural network to do the right thing, I'm computing the gradient, right, with respect to my weights. So in this case, the weight matrix would be this and the vector B, and of course, whatever matrix I have here, right? So here you have another matrix. So here my matrix is V, and here's my matrix W, and here's my matrix is V. Does that all make sense? Any more questions? This is good. These are good questions. So it's really, really simple, right? So every single layer, what I'm doing, I'm just taking the input from the previous layer and I'm multiplying it by a matrix. So, you literally do this, right? You take my X and multiply it by W, and I add a vector. Then what am I doing? I'm applying some nonlinear for example, the max was 0. And now I have my second representation. So this here is my input, and this here is my first hidden layer. Sorry, what is this nonsense? Okay, and now I multiply this with another bit, and I say, okay, well, let's call this C. And I apply another nonlinearity. Now I have a second hidden layer, right? In this case, this would be this hidden layer. I would add another hidden layer. And then I can apply another hidden layer, right? And I can do this as often as I want. I can make this as deep as I want. And each time is just another matrix multiplication. And matrix multiplication used to be really expensive, used to be a lot of computation. And that has changed. Matrix multiplication actually is the poster child of parallel computing. I don't know if you've heard about Strasson's algorithm and so on. So that's really something that has changed since 1964, is that people have figured out how to make matrix multiplication super, super fast, right? It's not like it used to be that it's kind of the computation is cubic with the dimension of the matrix, but it's actually not. It's actually much faster than that. If you do it parallel, you can make it really, really fast. Good. Any more questions? And just to be clear, then when you do gradient descent, you can learn all of these parameters, right? You basically take gradient descent with all of these parameters. Good. Thumbs up. Should we move on? Quick thumbs up for all those who are with me. Okay, good, good, good. All right, awesome. So I forgot where I was. I tried to tell you the story about neural networks, but maybe I just move on. So okay, good. Now the idea is, of course, here that we have an input vector x, and we can basically, our data somehow can be represented as a vector. Now, Una mentioned convolutional neural networks earlier, and so they're often called CNN or ConvNet. And what are CNNs and ConvNets? And they're actually from the 1980s. They're invented in Japan. And the idea is the following. Imagine you have a data like this, you have some data where things could shift around. So let me give you an example. So let's say I have, for example, an Apple Watch. Here I have an Apple Watch. And the Apple Watch is actually detecting if I'm running, if I'm walking or something. I don't know if you have such a watch. Like if I'm going to start running, it would say, hey, are you running? Can I record this as a workout or something, right? So how do they do this, right? And so basically they have some accelerometer or some sensors, and they basically measure my activities, right? So suddenly I'm doing this, and this here is very, very indicative for me running, right? Now, here comes the thing though, right? If I just take this data and I vectorize it, I would actually have like basically all these different input features, right? And I could put them into a neural network and say, what am I doing right now? I'm running. But imagine, I would run a little bit later, right? So then actually this input would look like this, and I would get the same input, but a little bit shifted, right? What would that mean if in my vector, right? Actually, that would look very, very different, right? Like all these different input dimensions, suddenly everything would shift in space, right? I would actually get a very different vector, right? And it would look nothing like the other vector, right? I have the same activity, but at a slightly different time, and it looks totally different, right? So what you do, what the problem is with this kind of scenario is that you need a lot of data. You basically need data when people kind of shift activity, shift activities in time. Like let's say, I move my arms, right, at a slightly different pace, right? I need new training data because it looks completely different. So convolutional neural networks address this challenge the following way. Actually, quick question. Does the problem make sense to everybody? Actually, in a minute, we will get to, if you have images, it's the same issue, right? Let's say here I have this guy, right? I want to classify, does this image contain a person? If I have the same image, right, and have the same dude in a slightly different position, right? What happens? Let's say I divide this up into pixels, right? And it used to be that people just take these pixels and just make them a vector, right? You basically say the first pixel is this dimension, second pixel is this dimension, and so on, right? And what you can see is that these two images look completely different, right? Like the pixels where this face is are completely different. These are these pixels, they're here empty, right? But the pixels where this face is are actually these pixels that are completely empty, right? So these two images have nothing in common. They look completely different. And the neural network would actually has to learn that that's a face and that's a face, right? And would have to see training data from faces in all possible positions to learn this, right? And so convolutional networks essentially address this problem, that things can just shift around inside the representation across these dimensions, right? And they're the same object. This isn't a same label. That's an assumption. It's a modeling assumption. Basically, I'm telling you my data has a very specific property. If I shift things around across these dimensions in this specific form, it doesn't change the label, right? We call this translation invariant. The label is translation invariant. So if I take the space and move it over here, right, my label doesn't change. Okay, and so, but it's a little bit easier to explain. Can you exploit CNN to take advantage of other invariances? Say Lorentz invariance. I don't know, because I don't know what Lorentz invariance is. But you essentially what you can do is, you can make them a little bit invariant to small rotations. Rotational example. Okay, good. Yes, you can a little bit. It can be a little bit rotation invariant. I will get to it in a minute. So let's get to this. Let's say I have data that's actually something like this, right? But there's some activity, and I'm saying, well, if this were to shift a little bit in time, right, that should be the same input. But I'm really, what I'm trying to find is something like, is there, right here, is there at some point, this is what I need, right? This here is, you're doing yoga. This is very, very, this is the yoga specific activity that my Apple Watch is now detecting, right? And if you had the same activity a little bit over here, you would still be doing yoga, right? Just in a slightly different, order. So, all right, here's the idea. You take your inputs and you just vectorize it, kind of essentially ignoring this. You just, basically all these different, kind of discretize this in some way. And these are my different dimensions. And now you have a neural network, but here's what you do. You say the first classifier that you're learning is still a linear classifier, but I'm not just taking the whole input as input, every single dimension. I'm just taking a few dimensions. So this guy basically, only takes, for example, the first 3 dimensions. That's it. And the second one only takes takes the next 3 dimensions. And this guy takes the next 3 dimensions. So you see, this is a much sparser connectivity, right? And now comes another kicker, right? That all of these actually have exactly the same weights. So all of these are actually the same classifier. So beforehand, we kind of each node, if you went back here, we see this one had W1, this one had W1, this one had W2, right? And this one had, this one down here had WM, right? They all had different weights. They were different classifiers, right? Here, actually, these guys are all the same classifier. So they're the same classifier and they're only operating locally. And why are we doing this, right? Because we are looking for certain patterns. They're basically saying, okay, we try to find something like this, right? And we look, is it here? Is it here? Is it here, right? And so on. So we kind of, it's kind of like, like a dog, like you're sniffing out, like, like for drugs or something, right? You're sniffing out a certain pattern. And you do this all the way until the bottom, saying, okay, here we have our last classifier. And then you can actually learn a different classifier. You can say, okay, well, now let's do this guy. Let's say, we do a second thing where we actually now say, okay, well, we do one more thing, a different classifier that sniffs out something else. And again, it just uses three different, until the last guy that just uses these. So each one of these classifiers just uses a very small local portion, and it's replicated many, many times, right? And all these replications use exactly the same weights. And so if you know a little bit about signal processing, what you're going to realize is, because they are linear classifiers, what does that really mean if I basically do a, I'm just applying a linear function to this, and then I'm applying the same linear function here, and I'm applying the same linear function here. That's actually a convolution operation. So this here is the output of the input convoluted, convolved with a fixed kernel, right? And that's essentially what it is. Now, we're almost there. So these guys basically tell us how much does this kernel respond? Like, are we finding some signal here? And now we do something else. We call something pooling. We actually just take the max of, for example, these three. And then we take the max of these three, and we just get two outputs. Why are we doing that? Because essentially, we're trying to find a signature. We're trying to find a certain, yoga-specific, activity. And we look, is it here? Is it here? Is it here? Right? That's what these guys are saying. If some number is large, that means, yes, we found it here. If it's no, we didn't find it, right? And then we take the max, because ultimately we don't care exactly where it is. And that's the key, actually. That's really, really, really important, right? It doesn't matter when exactly you started your yoga, right? The important thing is that we now know you're doing yoga, you're doing running or something, right? And so you basically have the max operator saying, okay, one of these found it, right? And here the same thing, you have a max operator. And the same thing is happening with images. So when you do ConvNets for images, you basically have an image. And basically what I'm doing is I'm saying my hidden representation is again an image. It has the shape of an image, where this is, each one of these are output of classifiers. But this classifier basically takes as input only these 4 pixels, right? That's this classifier. And this classifier here takes these 4 pixels as input, right? And then I'm doing this max pooling, where I'm now going to, a smaller image, and I'm just taking the max of those 4, right? And this is the max. So essentially what I'm doing is my first classifier is saying, let's say I'm trying to find faces, right? I may have some classifier that basically tries to find eyes, right? And where I take the eyes doesn't matter, right? I'm just trying to find, another one tries to find a mouth or something, right? And so you're basically saying, is this an eye? Is this an eye? Is this an eye? And then I'm doing a max and saying, okay, somewhere here is an eye, right? That's really important. And at the end, you run a classifier and saying, if I find an eye, if I find a mouth, if I find a nose, it's probably a face. So this here is my eye detector, for example. And then I have a second set of features that do the same thing, slightly different kernel, that may be your mouth detector. And then you have another set of features that may be your nose detector, etc. Question: what should be the optimum number of pixels for each classifier? I mean, if you need to reduce the computational cost of it at the same time, have a good prediction. It's a good question. It's exactly this. It's a trade-off. So the question is how high dimensional should the image be? And at some point, it really is a trade-off between how much detail do you need and how fast do you want to run. So often people just downsample images to 200 by 200 pixels or something, and that works pretty well. Does it work even if the size of the features is different in different images? That's a very good question. If suddenly I zoom in, right, and I see your face really, really big, actually it's not invariant to that, right? So these first things basically detect features of, for example, eyes, right? But they assume that the size is roughly the same, right? So it's not like you still need data of basically people zoomed in or people kind of far away, right? So that it learns maybe different detectors. So maybe here's kind of a zoomed in eye, right? In eye detector. So that's why you need many different feature extractors here. And we call these things channels, right? So each one of them basically learns a different feature representation. What about multi-level images? View of an image. For example, I see. Okay, good. You guys have, if you had invented this a couple of years ago, you'd be famous now. So someone actually came up with this before you, unfortunately. Yes, you actually can have basically low resolution images and then higher resolution images and even higher resolution images. And there's multiple reasons why you want to do this. You may actually want to maybe just go in the low resolution image and see if you can classify it. If you're uncertain, then you go to the high resolution, or you mix them. And you basically say, well, one actually tells me the overall more of a global perspective of the image, and the other one gives me more local details. And I combine those. So yes, there's all sorts of variants of convolutional neural networks that do this. Question by Benjamin: How does ensure multiple channels don't learn the same filter? Oh, do we ensure that multiple channels don't learn the same filter? Do we impose our knowledge on the weight initialization? Very good question. We just randomize, we do the same thing. This is a highly non-convex problem. So we just initialize these filters randomly. The cool thing is, and this is really, really interesting. Oh, sorry. This is really, really interesting that this layer here, right, learns basically, let's say this is a, whatever, 100 by 100 image. This also produces almost 100 by 100 representation, but actually only has a tiny kernel that it's learning, right? Maybe a 3 by 3 convolutional kernel that we are learning. So the number of parameters are very, very little. This means that we can actually learn many channels here, hundreds, right? And so essentially what we're doing is we just learn many, many, many channels, initialize them all randomly, and hope that the neural network will actually learn some good ones. And in fact, actually one paper that Una and I and Cole had together, where we're basically saying, okay, well, we learn initially just many, many of these channels, and we don't really know which ones are going to be good. And then we say the next layer is a linear classifier with L1 regularization that actually then filters out which one of these channels are actually useful. And that actually makes a convolutional network interpretable. Did that answer your question? I think so. Okay, any more questions? That's good. These are great questions. That's really, really good. Okay, so good. I think happy to move on. So I'm not going through the math. The math is actually, but the math is relatively straightforward. So just one more time, you have an image. You just have a convolutional kernel that you run over the image that gives you a new channel. You do this a bunch of times. Then you do this max pooling. And now, for each one of them, you get against a bunch of channels. And then you do the same thing again. You do convolutional, you do another convolutional layer. And typically what you do is a convolutional layer actually becomes a sum. You do convolution each one of these channels and you sum them up. That gives you a new channel here. So this way you can actually mix and match these different representations. One thing that's interesting about the max is that basically you're saying, I'm trying to take the face, I'm trying to take a nose, an eye or something. So if you're the following image, here's something, but you have an eye here or something, you have, a mouth up here, you have, well, this is just 1 second, you have an eye here, you have a mouth here, you have a nose here, and another eye here, right? The neural network actually would confidently say that's a face, right? Because it detects all the things. It detects an eye, a nose, a mouth and a nose. And because it's all translation invariant, right? It can't actually tell that that's not a face, right? But humans can. So that's actually an indication that we haven't quite nailed it yet, right? So clearly there's something else going on in our brains it's not just max pooling. And Jeff Hinton, actually, he's someone who really pushed the max pooling thing. And now actually he really regrets it. So he is actually someone who says it was a big mistake because it works so well. And it's really, really hard to get rid of it. Something works so well. The other reason is that we don't have a good alternative at the moment. So this is kind of the best thing we have. Okay, good. This is actually, there's no more questions. I want to switch topic and go to data visualization. So you also want to talk about t-SNE and PCA. So if there's no more questions, I move on from CNNs to dimensionality reduction. Visualization. Okay, everybody take a deep breath. So if you actually got lost, this is a great time to come back because I'm now talking about something totally different. I'm talking about data visualization. So when we do machine learning, our data is usually in some very high dimensional space. D, and this is capital D because it's so high, right? So I'm making a big D. And our data is up here, right? And we're trying to learn them. And now the interesting thing about this is though, like the problem is like, for us humans, high dimensional space is always a little intimidating. So if you have 100,000 dimensions, it's hard for us to kind of get a good grasp of it. Because obviously we're tuned for 3 dimensions, right? So you're kind of a little bit defunct, right? The good news, though, is that most of the time, data actually, when it's in high-dimensional space, it actually doesn't really live in a high-dimensional space. Why is that? Because if it's interesting, it has to have some structure, right? If the data doesn't have structure, then you can't learn anything. Then it's just uniform noise, right? That's not very interesting. So the only reason we are interested, the only reason we are actually working with data is because it has structure. We're trying to learn the structure, right? And if it has structure, then it's probably not actually high dimensional. And so I can give you an example. So let's say faces, right? Images, right? Natural images. You know, we have these pixels, right? As we were talking about them. And let's say you have a camera, whatever. Your iPhone has, I don't know how many megapixels, 6 megapixels. Well, it probably has a lot more, right? 6 million pixels. Each one has 3 colors. So that's, what does that mean? You line in, you line in 18-dimensional space, right? So 18 million, right? So 6 million pixels times 3 colors is 18 million. And so I guess pixels can't be negative. So really you line a 0, 1 space to the power of 18 million, right? That is massive, right? It's really, really high dimensional, right? And but actually, if you were to now take such an image and you would just randomly sample, you know, you could say like, hey, here's a great idea, right? I can just sample images from the space, right? I can just take pixels and assign random colors to them. And every time I do this, I'm gonna see a picture, right? And this is really, really cool because this actually allows me to see things that I can't even see, right? I can make my own magical camera, right? And I can look on Mars. I can look at Venus, Jupiter, or something, right? And just randomly sample images. And eventually, I will see an image that's, you know, whatever, the surface of Mars, right? Despite that I've never been there. Why doesn't that work? Because the probability of seeing that is essentially 0, right? Because actually, if you would just randomly assign colors to these pixels, you would actually always see noise, right? In fact, you would actually probably your entire life, you know, if you think about this, right? The number of, you know, this is so high, right? This is way higher than the number of electrons in the universe, right? You would never see anything interesting. So what does that really mean? That means in this very, very high dimensional space, there's actually only a very, very small region that corresponds to natural images, right? Almost all of it is just nonsense. It's just nothing, right? Okay, so it would be nice if we could somehow reduce this dimensionality, ideally actually to 3-dimensional space that we can visualize it, or reduce to a more manageable space, like maybe 100 dimensions or so, that our algorithms work faster. We can kind of, the curse of dimensionality doesn't bite us and stuff. And there's many different ways of doing this. And the most common one is PCA, principal component analysis. And PCA is such a good algorithm that in fact it was invented 5 times, I think. So it's actually the same thing essentially as SVD, singular value decomposition. It's the same thing as multidimensional scaling, more or less. And it's the same as the KL transform. Is that 5? Yeah, that's 5. No, 4. Okay, well, there's a few others, actually. I've at least invented it a couple of times when I kind of came up with a really cool algorithm, then I'm like, it's just PCA. So, you know, it gets reinvented all the time. And principal component analysis essentially says, okay, well, assume we have our data in some very high dimensional space, right? But maybe there's a low dimensional subspace. In this case, maybe this plane. And all our data lies on this plane, right? It doesn't actually, we don't need all these other dimensions, right? D may be 100,000, but actually it's only 2-dimensional, right? You just have some additional dimensions that really don't mean anything. And you can't tell because it's just not axis aligned, right? So you can't tell that actually everything's just going on in 2 dimensions because these 2 dimensions kind of, you know, a combination of many different dimensions in your representation. So what PCA does, actually, can I ask a quick question? Who knows PCA? Raise your hand. This is like, I'm not sure. Okay, right now we have 3 people know it. A lot of people know it. Okay, so let me actually maybe Actually, more and more people know it. Okay, good. People are coming out of the closet, admitting it. All right, good, good. So what does PCA do? It essentially, we just do the following. It's very, very simple. We just assume the data is centered. This is very simple. We can always just subtract the mean, right? So we can just say, okay, we have a new coordinate system that actually is right in the center. And then what we are trying to do, we're trying to find directions. We try to find these directions of this hyperplane, basically. And the first direction is the one of maximum spread. Actually, in this case, it would be this dimension here. And the second one is this dimension. And the third dimension now is this. And how do we do this? Well, you know what? Let me just go over this in the interest of time. I just give you the intuition. I'm not gonna go too much into the details. The idea is basically, there's actually one reason PCA was invented so many times is because there's many different ways of deriving it, and it's really, really cool. So if you basically say, I want to find the direction of maximum variance, right? Where do I have the maximum spread in my data? That gives me PCA. But you can also say, you know, I would like to have the direction, so a low dimension subspace, that if I take my data and project it in the subspace and I reconstruct it, I minimize my error. Just to show this, it would mean the following. I have some data and I have some direction here. And I'm basically saying I'm minimizing this error, right? This is the projection error. So I'm projecting onto this hyperplane. If I go back, I want to minimize this, which is different than linear squared, least squared, because least squares minimizes this error, right? If this was y. Whereas PCA just says we're in some high dimensional space and we have some hyperplane and we minimize the projection error. That's the same. So it's not exactly the same algorithm. And there's also some information theoretic derivation that, again, you know, leads you to the same algorithm. Okay, so, but ultimately, the design constraint here is basically I'm trying to find a linear subspace that actually essentially explains most of my variance. That basically, you know, I'm trying to find the linear subspace, some dimensions, which capture most of my data. And the way this, well, the way this works is I can basically, you know, well, let me give you a one-line derivation. Xi goes to V transpose Xi, right? So V here is basically my projection onto some direction. This is just direction, so I can say V transpose V equals 1. And so what I would like to do is I want to maximize sum of V transpose Xi squared. Right? So that's just the variance. I'm basically saying if I project all my data onto this direction, I want to have really large spread, right? And you can see that this direction here would be really, really good, right? Because the spread goes from here to here, so I have a very large variance. If instead I would project onto a direction that's like this, then all the points would kind of just be, you know, be within the, you know, they would all be here as a very little variance, right? And if you, you know, complete the square, you know, then essentially what you're getting is Xi transpose V. Oh, sorry. Switch these around. V transpose Xi transpose V. And what is this? Well, this is just 1 over n, V transpose I, Xi transpose V. And this is our covariance matrix. So what I'm maximizing is V transpose V, such that V transpose V equals 1. And this is just the eigenvector of the covariance matrix. So PCA is one reason people love PCA is because what you do is you just compute the covariance matrix C equals sum over I Xi transpose, and you compute its eigenvectors, and bam, right? You have the answer. So it's really, really fast. So you just, you know, it's a really, really simple. It's like one line of Python, right? It's trivial. So you can always do this. And the nice thing is if you look at the eigenvalues of this covariance matrix, they actually tell you exactly. So the leading eigenvector basically is the first principal component, second eigenvector is the second one, and so on. And the first leading eigenvalue tells you exactly how much variance you have in this direction. So what you do is you look at these eigenvalues, and you have basically look at the first one and the second one and the third one, fourth one, fifth one. And here, in this case, for example, you could tell, okay, there's really only 2 dimensions because the other ones have very little variance. So most of what's going on is in my first 2 dimensions. I said that's the same thing as SVD. Well, if you take your covariance matrix and you just write this as USV transpose, you just decompose it with SVD, then actually what you're getting is the following. This here is actually, these are the principal components. So that's actually the answer of PCA. And the V is just U times X. So this is basically the data projected onto the principal components. So you can, so if you just, you just take, so when people say to the SVD of the data, it's a little bit weird thing to say. It doesn't really make sense because SVD is really a decomposition of a matrix. But what they really mean is I do PCA. So I take my covariance matrix and I decompose it in this way. And this basically tells me the diagonals in the S matrix tell me how much variance I have in each dimension. It's the square root thereof, actually the standard deviation. These here show me the directions. And this here is the data projected onto the directions. So that's what SVD gives you. Any questions? No. All right. Good. So I think people are happy. People know PCA. So now what about nonlinear PCA? And now we have a few minutes. So is the way a computer computes PCA and SVD the same? Yes, essentially behind the. I mean, you can just do PCA, but compute the covariance matrix and call SVD on the covariance matrix, and that's essentially you get PCA. Okay, so about 20 years ago, actually, when I started my PhD, there was a big race, and the race was the following. They basically said, well, we all know PCA and we love PCA. PCA is awesome, but what if your data lies in something like this? Well, actually, let me draw this. What if your data lies on something that's like this, like a Swiss roll or something, where basically I have data that's essentially on a manifold. And this is really 2-dimensional data, right? Like if I were to give you the coordinates of each point, I would just have to tell you this direction and this direction, right? Along this manifold, right? How can I find this position? And but PCA would not work, right? Because there is no subspace. It's actually a manifold, right? And so the question is, can we somehow extend PCA to something nonlinear? And back then there was a big race, and there was a big frenzy in machine learning. Everybody wanted to figure out how to do it. And in fact, actually, I also threw my head in the game. My half of my PhD thesis is actually on some algorithm to do this. And essentially, they all kind of have the same flavor. What we're doing is we basically take these data points and we build a nearest neighbor graph. So we connect each data point to its k nearest neighbors. Why? Because a local nearest neighbor graph is a really good approximation of this map, right? You basically then, what you get is something like this. Well, let me do this. You have these points, and we basically connect them, right? And so this graph, essentially spans the same, spans this manifold, right? Because it's only local connections. And let me just tell you a few algorithms that came out of this. So the first algorithm I think came out of this was isomap. I don't know if anyone has heard of this. Isomap does the following. Is from Josh Tannenbaum, now at MIT. And his idea was the following. We just built this nearest neighbor graph. And then we measure the distance between any 2 points as the graph distance along this graph, right? So shortest path. So you just compute the Dijkstra's algorithm, which is an algorithm that gives you the shortest path. You know this all from GPS, right? When you say, I want to get directions to Boston or something, right? Basically, it has a big graph where the nodes are the roads, and it says what's the shortest path. And you build a distance matrix that basically tells you, here the difference between ijth entry is the graph distance between node I and node J. along this graph. And then essentially, when you have a distance matrix, you can actually convert, you can essentially do PCA on a distance matrix. So you do PCA. So what does that tell you? That gives you a Euclidean space in which I and j, the distance between I and j, the Euclidean distance, is this distance. So you can basically take this data that lies on a curved manifold and project it into a Euclidean space. Very cute idea. I thought it was pretty awesome. Works really well. Has some problems. If you, for example, have a hole here, then the path goes around it, and you distort the whole thing. So that was, one reason, one limitation of this. Another algorithm is local linear embedding. Local linear embedding says, okay, we take data points that are kind of what we do. We take nearest neighbors, and we reconstruct each point from its nearest neighbors. And then we map them into a low-dimensional space, where in this low-dimensional space, if I were to reconstruct, and I place all my points here, and I reconstruct each point from its nearest neighbors using the same weights as I would do in the high-dimensional space, I'm basically saying here, xi equals the sum over all my neighbors, wij xj. So I'm learning these weights. So I'm basically can view this as I'm cutting up this into many little patches. And I'm saying in the low dimensional space, I should have exactly the same reconstruction rule. That was local linear embedding. It's also very, very cute algorithm. And it's again but all of these have their upsides and downsides. Just because it's me, I tell you my algorithm, maximum variance unfolding. So the algorithm that I came up with was the following. We take these data points, we build a nearest neighbor graph, and then what we do is we try to maximize the variance. So we can move the points around, but you can, so imagine you had a sheet of paper here. I have this sheet of paper, I've drawn a bunch of points on it. It's kind of crinkled up, and I'm basically unfolding it by maximizing the variance. But the trick is that any 2 points that are connected cannot increase in distance. So basically, I'm making kind of rods, right, between any 2 points and their neighbors. And I'm saying that distance can't increase, but overall I can increase. So something, let's say I have this in the high dimensional space. This could become this, right? So basically, these local distances stay the same, but actually I can globally unfold it. And so again, here we learn a matrix by maximizing the doing this transformation as an optimization, and then we run PCA on this inner product matrix. That's and we learn basically a matrix that we first spread everything out, and then we do PCA on this. Okay, good. But actually, all of these are great algorithms. But I think the person who really nailed it was Lawrence van der Matten, and he actually invented t-SNE. And t-SNE, essentially, and I guess my claim to fame is that I almost that I inspired Lawrence to invent t-SNE. And so he had the brilliant idea. His idea was the following: that he basically said, okay, here's what we do. We do the same thing, but we take the data points and we build a stochastic. We put a Gaussian around each data point, and we assume that the neighbors in this graph are drawn randomly. So I basically take each data point. It's like this, right? In this low dimensional space, you can see it better. So here we have a Gaussian, right? Let me see. What's the probability that I draw this guy as the nearest neighbor? What if I draw this guy as the nearest neighbor, or this guy, or this guy? And in the low dimensional representation, I want these probabilities to be the same. So I want basically, if I place this point somewhere, I want this guy, I want to place it such that the probability that I draw it as nearest neighbor is the same as in the high dimensional space. And that's essentially the idea. So does that make sense? So every data point has some nearest neighbors. And I'm making that stochastic. I say, I put a distribution around this data point, and I'm drawing nearest neighbors at random. And in high dimensional space, that's happening. I just put a Gaussian there around every single data point. And then I go in low dimensional space and I place the points, now constrained to just being in 3D, such that if I put a point and I put a nearest neighbor next to it, the probability that I would draw this guy as the nearest neighbor stays the same as in the high dimensional point. And so what does that mean? Well, if in the high dimensional space, if I have a point here, sorry, a point here and a point that's really far away, the probability that this guy is my nearest neighbor is 0, right? Because I have a Gaussian here. This is 0, right? Or a Gaussian would be like look like this. So I can place these anywhere I want in relation with each other. There's no constraint. But if points are close, right, then they actually have to be close in a low dimensional space because they should still be likely as nearest neighbor. And there's a problem though. The problem is that if I go from a high dimensional space, there's many different ways of placing nearest neighbors into a low dimensional space. This doesn't work, right? Because I'm no constraint. I had 100,000 dimensions. Now I have 3 dimensions. How can I put all my nearest neighbors in 3 dimensions such that they are equally likely to be nearest neighbors? And the genius thing that Lawrence van der Maten came up with was that he has a Gaussian distribution in a high dimensional space and a student T distribution in a low dimensional space. And student T distribution is very similar to a Gaussian, but has heavy tails. So you can shove the data points into the tails, which you cannot do in the high dimensional space. So in the high dimensional space, they're basically close by. In the low dimensional space, you kind of have a little bit more, you have fewer dimensions. So you don't have so many directions in which you can move them, but you have heavier tails. You can move them in the tails. It's a little like when your parents come to visit in your dorm room, looks like a mess, right? So what you do is you just put things under the carpet or under the, you just hide things, right? That's what you can do in the low dimensional space. And that's why it's called t-SNE. So t-SNE here stands for, student T stochastic neighborhood embedding. And a brilliant algorithm, and maybe I can now show you a little 2-minute demo. Otherwise, Andrew is going to get mad at me.
We started 5 minutes late. I will defend you against Andrew.
Okay, good. Andrew's wrath is gonna hit me. 1 second. Here. Okay. Good. Can you see this? So actually, this is a demo that someone else made online. I just found it and I thought it was very, very cute. So here's actually data that's drawn from a very high. You can play with this yourself. Distill.pub. Here's data that's drawn in a very high dimensional space, but it comes from a grid. And so if you visualize this with t-SNE in 2D, you actually recover this grid very, very nicely, right? Another thing here, for example, we have 2 clusters, right? And these could be Gaussians or something in a high dimensional space. And t-SNE basically shows them in 2D very, very nicely as these 2 clusters. One thing I just want to say, and this is very, very often misunderstood about t-SNE. t-SNE tells me, like, if this cluster is how far away that is from this cluster, that means nothing, means absolutely nothing, right? Because they all have 0 probability of being neighbors, right? So globally, t-SNE gives you 0 guarantees, right? Let's say you have 3 clusters, right? And I have 1 cluster here, 1 cluster here, 1 cluster here, and this cluster. The fact that this one is closer to that one doesn't mean anything, right? Because t-SNE doesn't do any global optimization. It's just local, but it tells me that this guy is very similar to that guy. They must be close together, right? The fact that it puts them so close together tells you that basically in the high dimension space, they must be close together, right? That's what t-SNE does. Here's a few more. So here they actually have 2 rings that are kind of interlocked, and t-SNE actually, separates these 2 rings, right? Because globally, like despite that actually in the high dimensional space, they're kind of interlinked, right? If you just locally, these are not interlinked, right? These guys are kind of nearest neighbors, and it managed to capture this very, very nicely, right? So in 2D, basically, the fact that you have these rings that are kind of going inside each other goes away, and you just have 2 rings, right? But it tells you exactly this guy is really close to this and this guy, and it's closer than to these other guys, right? It does. The fact that this guy is closer to that guy than to that guy really doesn't tell you a whole lot, right? Because they both have 0 probability of being neighbor from this point. But of course, it's so nice that basically you get this nice ring structure, so homogeneous. Let me just make sure that I can see actually the questions in case someone has some. Okay, actually, Una, can you, in case someone has a question, maybe.
Yes, I can monitor. Yep.
Okay, good. All right, good stuff. So this is, so PCA is a very, very nice tool to actually, if you have data projected in a low dimensional space, if you're lucky and it's really low dimensional, right? t-SNE is really, really good at visualization. It's not good at anything else, right? So if you reduce your data with t-SNE, typically you can't really run any algorithms on it in the low dimensional space. That doesn't really, because you lose too much information, right? You only keep the local structure. It's too little, right? Too little information. So PCA is great to reduce data, like go from 100,000 dimensions to maybe 100 dimensions, then run an algorithm over it. t-SNE is really, really good to take high dimensional data and project into 3D to see, do you have cluster structure? Is there something interesting going on?
There's a question.
Yeah.
Is the dimension of the target space a parameter that you specify, or is it determined by the algorithm automatically from Ivan?
So very good point. So in PCA, you get these eigenvalues that basically tells you how much load you have in each dimension, and you can cut off at any time. And basically you realize, okay, I'm capturing 90% of the variance now, right? So 90% of the variance is in these first 2-3 dimensions or something. You can do 50 dimensions. With t-SNE, it's just a design parameter. You're saying I'm taking this high dimensional data, I'm mapping to a low dimensional space, and I'm that's essentially what it is, right? and you specify that up front. And usually you pick 2 or 3 because that's what we humans can comprehend. Okay, any more questions? If not, actually,
could you give us some examples of structures you learned from t-SNE, or other than simply use it for classification?
Yeah, so for example, here's actually the original paper, and I can show you this very nicely. This is the GMMs data set, where you actually have handwritten digits, and you can actually see here, basically, it shows you very nicely these different, different clusters of these various different, I think this is the MNIST data. This is MNIST? Yeah, it's 6,000 handwritten digits. So it shows you these different clusters of these different digits, right? So you can actually see, oh yeah, there is different clusters. The cool thing actually is, you take this data set, and you just take one digit, for example, the 2s, handwritten 2s, and you visualize it with t-SNE, you actually get 2 different clusters. And initially people didn't know what it was. And then they realized that actually the data set was collected at 2 different high schools, where they asked high school students to write digits, and they used 2 different pens. And so one was thicker than the other. And that's actually what you get. So that's something that wasn't known until people visualized it and discovered it then. But that's essentially what it is, right? It's just for you to kind of look at the data, get intuition, like, are there clusters, is it kind of all mixed, etc. This kind of stuff. If you have a few more minutes, then I can actually show you a cute little animation. This is kind of a little bit like a, let me just, 1 second.
You're muted, Kilian. You're muted.
Can you hear me now?
Yep.
Okay.
Yep.
Okay, good. I just because I have this. Okay, now it's better?
Yep.
Okay. 1 second. I have, because I just told you the story of this dimensional reduction race. So here's like a 3-minute skit. I don't know. Hope Andrew, hope you don't mind. So this was actually after my PhD. We had a workshop at NeurIPS, and we tried to say, 1 second, can I somehow mute this? No. I can just get out of here. 1 second. Okay, and we had a workshop at NeurIPS where we tried to, analyze, where have we gotten in the race? And this was right before t-SNE was invented. So we had all these different algorithms. And so you can see here, actually, this was me, kind of the younger version of me, 16 years ago. And I was actually just, this was the summary presentation that we gave. And I was obviously trying to get a postdoc position. So advertising this. But back then, we did a little bit of an analysis, and we looked into what are the data sets that people use to test their dimensionality reduction algorithms. And so we looked at all these different papers, and we realized actually they all use the same Swiss roll data set. So actually everybody, like the entire community, actually overfitted to this data set. But everybody just used these Swiss rolls, which we got really good at as a community. We could nail the Swiss roll, but it seemed a little bit artificial. And so the conclusion was like, the problem is we've kind of moved off into this, everything is synthetic. Can't we just have some more real world data set? And so what I proposed is, why don't we just use the cinnamon roll? Cinnamon roll is, a lot more tasty and more real. And so I tried to actually use these different algorithms on the cinnamon roll. And so the first thing was my own algorithm, which is this maximum variance unfolding. I told you this, like basically you unfold the data set. And so I tried to do this with the cinnamon roll. This is how it works. Roll it, roll it, roll it, roll it, roll it, roll it, roll it. So this is how it works. And another one is local linear embedding, which is basically, and I told you this, is chops it up in a high dimensional space and then reconstructs it. So here's the and that, of course, you could, can use all these different nonlinear algorithms, but why don't we just use a linear algorithm? Sometimes that may work really well too. So what if you do principal component analysis? That essentially is a projection in low dimensional space. We can try this here. So this PCA projection. And of course, the nice thing about PCA is you can reconstruct the original data. So here you can see the reconstruction. And I made my co-author eat the whole thing. Anyway, that was the summary of our workshop back then. And with that, I conclude my mini lecture series. And thanks, everybody. And I hand it over to Andrew.
All right.
Thank you, Kilian. Thank you so much. I can't believe you have a slide from 16 years ago.
It's amazing it still works.
It's timeless.
I think I was doing view tabs. I don't know where they are. That's incredible. All right. Well, thank you, Kilian. Thank you so much. Before we bring Andrew in, I want to share one link. This is a brief survey, exit survey. There are only 3 questions and 1 optional question. It would really, really help us to get this feedback, because the whole platform using Gather Town and that was not free. And we were supported by NSF funding, and our sponsors always want to know how the workshop summer school experience was like for the participants. And there is also a very important question about demographics. The survey is anonymous. We would really, really appreciate it if you take, a minute at some point and answer the survey, and it will really help us. All right, so without any more, Andrew's going to now take us to the adventure of GP, I believe. Andrew,
so it's good to end on a note of how everything is really Bayesian. And so we're going to be talking about how everything we've discussed relating to machine learning has not just a Bayesian interpretation, but can be really unified together from a Bayesian or at least a probabilistic perspective. And today's talk will have an emphasis on unsupervised learning, just kind of for cohesion with what Kilian has discussed just now. Okay, so let's share the screen. Oh, my iPad also needs to be a host, I guess. Maybe I can make it a host. Let's see. Is someone able to make my iPad a host? There's 2 Andrews.
Jonathan, can you make second Andrew the host as well? I'm not sure if I can do that, because I'm also a co-host.
All right, that looks like it worked. Thank you. All right. So unsupervised learning. This is from a probabilistic perspective. So often if you take an ML class, when you get to the unit on unsupervised learning, it's broken down into a bunch of subunits. So these include clustering, which we'll talk about mostly today, density estimation, dimensionality reduction, and let's put this down here, generative modeling. So examples of clustering would be k-means, which we'll introduce shortly. There's hierarchical clustering methods like agglomerative clustering. Density estimation. So today we're going to talk a bit about estimating mixtures of Gaussians. The coin toss example we considered last time was also a special case of density estimation. We were actually trying to estimate a binomial distribution in this case. What is the bias of that coin? Even though it may not have seemed like it because we had heads and tails, etc. That was an instance of unsupervised learning. We were just sampling from a discrete distribution, and we still have observations. Not having labels doesn't mean we don't get to see the data. It just doesn't mean it just means that someone hasn't manually annotated it. So mixtures of Gaussians, we could sort of the coin example. There are lots of examples. And in fact, we'll see a bit today how everything is really density estimation in a sense. Dimensionality reduction. So there's PCA, there's t-SNE. There's sort of a whole field of manifold learning, which is what Kilian did his PhD thesis in. If you want like other types of nonlinear dimensionality reduction, you can use neural network models called autoencoders. So lots of examples. And generative modeling, some of you may have heard of GMMs, variational autoencoders, models called normalizing flows. And what I'm going to try to emphasize today is that all of these things are all really just different sides of the same coin. We can use one formulation to derive all of these methods. And it's not even necessarily that abstract. It's basically just a basic mechanical procedure that we've already started to get comfortable using when we were thinking about things like regression, the coin toss example. I gave another example of classification, where we wanted to start with an observation model, use that to create a likelihood for binary classification, and then maximize that likelihood to train our model. Really, the mechanics of all of these things are exactly like that, and we'll see how in just a moment. So let's start with density estimation. So let's suppose we have some points, we'll call them x1 up to xn. Sometimes I've been calling these y's. Here, let's just stick with x, and we'll assume they're drawn from some distribution. Px. Now, our goal in density estimation is to estimate the Px by creating an observation model Qx, and the observation model might have some parameters theta, from which we assume the xi are drawn, and then our learning task is to estimate theta, these parameters of this observation model. So let's consider a few concrete examples of this. So let's say we just have a bunch of points. Let's be pretty abstract. They could be like people's heights, whatever we like. And we assume that they're drawn from some distribution. So maybe it's a Gaussian distribution, maybe it's something totally different. But let's just suppose, for the sake of argument, that we believe that these points have been drawn from a Gaussian distribution, but we don't know the parameters of that distribution. So we don't know its mean, we don't know its covariance matrix. So let's assume this is our observation model, Px equals Nx. Mu is the mean of the Gaussian, and sigma here is the covariance matrix. So I'm assuming that these measurements that we're taking are multivariate. Okay, so we want to estimate mu and sigma. So step one, just like before, let's create our likelihood. So the probability of the data, given these parameters, if we assume that they've been sampled independently from this distribution, given the parameters that we have, is just going to be a product over the xi's. Which is going to equal product from I equals 1 to n of our Gaussian density and we already got a little bit of exercise writing these things down when we were thinking about how to derive squared loss, but let's just take the log of that density again. And so that's going to be equal to minus nd over 2 log 2 pi minus n over 2 log determinant of our covariance matrix minus 1/2 n equals 1 to n xn minus mu transpose sigma inverse xn minus mu. Okay, so all I've done is written down the log density for this multivariate Gaussian distribution when we've created our likelihood for our endpoints. So if you're taking a while to parse this, it's really very simple. We just have a bunch of points. We assume they're drawn from a single Gaussian. We can use that assumption to create our likelihood. What is the probability of observing all of these points given the parameters we're trying to estimate? And then if we're doing maximum likelihood, all we do is find argmax over mu and sigma, P of D given mu and sigma. All right, so we can take derivatives and so on and set them equal to 0. And maybe we could do that very quickly for mu. So we can also take derivatives with respect to vectors if we like. And so that's going to equal mu. If we set that equal to 0 and kind of confirm we have an optimum, then we get mu ml equals sum of our points over the total number of points. All right, so let's do a bit of a sanity check here. Does this seem reasonable to you? Yes or no? Why? Why is it reasonable? Right. So let's try to make sure that we have some context for what we're doing here. I said, like, we're measuring everyone's heights, for instance. I'm assuming it's drawn from a Gaussian distribution. Now I'm trying to estimate the parameters of this distribution. Mu is the mean of that distribution. If I go ahead and create my likelihood and then maximize that likelihood with respect to the mean, then basically what I get is the empirical mean of my measurements. So the sum of my measurements divided by the total number of measurements. So that seems pretty reasonable to me. We might be a little bit scared to say that something is reasonable after seeing the coin toss example, because the m over n number of tails over total number of flips seemed kind of reasonable until it wasn't. But I'll give you this. I think this is a reasonable estimator. And we can go ahead and take derivatives with respect to the covariance matrix too, and get an estimator that looks like this. Now, this is actually pretty reasonable as well. It's slightly biased in the sense that the expectation of sigma tilde here is actually going to be slightly less than the true value of sigma, but then we can just multiply this estimator if we want. Oh, sorry. I've already done that in the expression. This would be 1 over n. This is sigma ml. All right, and then so that way we can just try to multiply by n over n minus 1 and form a sigma tilde that's equals n over n minus 1 times sigma ml. And now we've got an unbiased estimator. Okay, so you've probably seen something like this before if you've taken an intro to stats course. Like if you're estimating the parameters of a Gaussian, you can take the empirical mean, and then you can take the empirical variance, but there might be this little correction factor to keep things unbiased. Okay, so that's all fine. Now let's make our model slightly more flexible. Let's assume that these points, x1 up to xn, have now been drawn from a mixture of Gaussians. So let's assume that Px, and let's just keep things one-dimensional so it's really clean and easy to see everything that's going on, is equal to W1 times a Gaussian in X, mu sigma squared, mu1 sigma squared, say, plus W2 n X mu2 sigma 2 squared. All right, why would we want to do this? Well, it's a more flexible model. Let's suppose that the data that we're measuring is actually bimodal, for instance. Like maybe we're taking the heights of men and women in the room and they follow a somewhat different distribution. So we want to capture both modes of the distribution. We want to use a more flexible approach. And in fact, if we use an arbitrary number of components in a Gaussian mixture model, we can estimate any distribution to arbitrary precision. Great. So we've got a more flexible model, but let's follow exactly the same mechanical procedure and now form our likelihood. So just to be kind of super careful, we could call this P of X given theta, where theta are all the parameters that we want to estimate: W1, W2, mu1, sigma 1, mu2, sigma 2. All right. So what is our likelihood? Well, given the parameters, we can say that everything is IID. It's important that I'm making this IID assumption given the parameters, by the way, because if I didn't condition on the parameters and everything was actually independent, there's really not much we could do. We basically would just have noise. So for example, if I say I'm drawing from some distribution and one of the numbers that I draw, let's say I draw a number and it's like 10 million, and I assume that this is drawn from a Gaussian distribution, and I said, do you have any guess as to what the next number might be? You would probably think, okay, it's probably going to be a large number. That seeing that big observation might suggest either the mean of the distribution or the variance of the distribution is really big. And so in this sense, our data points are not independent at all. But then if I say, well, actually that first point was drawn from a Gaussian and its mean was 10,000,001 and its variance was 5. And now we're drawing another point. It's safe to say, okay, that second point is independent of the first point. All right, so let's write down the full density here. So we've got square root of 2 pi sigma 1 squared x of minus 1 over 2 sigma 1 squared xi minus mu1 squared plus, and this is all inside the product, w2 over square root 2 pi sigma 2 squared exp minus 1 over 2 sigma 2 squared xi minus mu2 squared. All right. Now, my question to you is, can you, just eyeballing this expression, don't think about taking derivatives or anything else, and let's just forget about W1 and W2. Let's not worry about estimating those. Can you see a configuration of mu1, sigma 1, mu2, sigma 2, which will give us very good, i.e. infinite, likelihood P d given theta? So if we just look at this expression and we play around with it a little bit, can we come up with some setting of those parameters which will give us really, really good likelihood? Maybe just take a minute and think about it. And one way to quickly see an answer is to try to simplify the expression by choosing a nice value for one of the means. Okay, so what happens? Means of the Gaussian be the maximums of px given theta. Well, I don't know. Let's sort of unpack this. So with this product of terms, let's let mu1 equal one of the points that we observe. Let's say xj, where xj is just some point in this collection of data points that we've observed. And so if we look at that term where I equals j, the x for that term will just disappear. And we're left with, so if we look at the term for I equals j, we get w1 over square root 2 pi sigma 1 squared plus w2 over square root 2 pi sigma 2 squared exp of minus 1 over 2 sigma 2 squared xj minus mu2. All right. So now what can we do to sigma 1 to make this expression really, really large? Small number, yes. So let sigma 1 go to 0. So in that case, this first term will just blow up. It'll go to infinity. And the other terms in the product will not be 0 because we have this second component, which is giving some positive value to all of those terms. So I'm letting mu2 sigma 2 be kind of whatever, just some positive numbers. And this model then is saying, okay, well, for every point but xj, I've got this second component and it's giving, some probability to those points. And then for xj, I've got this first component and it's giving that point infinite probability. And so this is a setting of parameters which will optimize our likelihood. We can see that just by looking at the expression for the likelihood. But is it a setting of parameters that we believe? Is this behavior that we would want? No, why not? Isn't P d given theta constrained to be between 0 and 1? That's a good question. The answer is no, because here we're not talking about an actual probability. We're talking about a probability density. And so the integral of P of D given theta with respect to D has to be 1. But the actual values of the density can be very, very large. Okay, so if we were to visualize our fit for the distribution, it would look, in this case, like a point mass and then some Gaussian that's sort of covering the rest of the points. And let's say this is where we've kind of observed our data. Now, of course, this is not really a density estimator that we would believe in. In fact, if we keep adding more and more components to this model, we can really please the likelihood just by collapsing all of those components onto single data points. But if we imagine this as a generative model, so let's say we're actually trying to sample new points from this distribution that we've used to estimate the points that we have observed, all it's going to do is repeat the points that we've already seen. And that's probably not what we believe. So if we wanted, say, a distribution over people's heights, and we took a bunch of measurements, and then we estimated this model, and it basically was just a sequence of point masses at all the measurements that we've taken. If we wanted to generate more points from this distribution, we would just be repeating ourselves, which of course is opposed to what we actually believe. And so this is an instance of where another instance, maybe even more obvious in the coin toss example, where maximum likelihood is clearly pathological. It's clearly not giving us what I want, or what we want in maximizing the likelihood. And the reason that we didn't see this pathology when we were estimating just a single Gaussian is because if we had collapsed that single Gaussian onto just one point, well, the term in our product for that one point might be very happy, it might be infinite. All the other terms would be going to 0 exponentially quickly. So that wouldn't actually be a solution that would overall give us a good likelihood. In the mixture setting, basically we have this other component, which is giving us some probability for all of those points, which is why we can then realize this pathology where the variance goes to 0. And it's actually kind of insane. So this is a real problem with doing mixture, like just density estimation in general. And often the practical prescription for this, if anyone kind of encounters it or asks about it, is, well, just run the procedure again and hope you get trapped in a local optima that like isn't that solution. And so it's pretty crazy. Like it's like the objective itself is not really aligned with what we're trying to do, and we're just hoping that we don't do a good job of optimizing it in practice, so that we don't actually discover this solution that has high likelihood. Of course, the resolution is to not do maximum likelihood, to just kind of completely follow the rules of probability and do a Bayesian model average. And interestingly, when you do that, so the resolution here would just be specify a prior on theta. And then if we want the density for any point px, we just integrate px given theta, p theta given d theta, where p theta given d is our posterior. And when we follow this formulation, we actually can very naturally use models with even an infinite number of components and often achieve very reasonable looking density estimators. So an example of this would be the Dirichlet process mixture model. And there's a really nice paper called the Infinite Gaussian Mixture Model. By Carl Rasmussen, who is also one of the authors of the famous book on Gaussian processes. And he just kind of derives this model from scratch. You take a few limits and it comes out very naturally. And with this formulation, you now have both a very, very flexible model, one that's actually capable of estimating any distribution to arbitrary precision, but also one that doesn't tend to overfit, that provides reasonable generalization. And from this perspective, it's even okay to include some settings of parameters that are point masses, as long as those solutions don't take up all of our posterior probability. So that's sort of a couple examples of density estimation. And we'll now see how principal components analysis, an approach that Kilian just introduced, is a special case of density estimation. So let's do a quick review of PCA. How do we figure out the posterior? That's a good question. So what we would typically do is start with a prior. Quite often, we might choose something like, so theta would include like the mu's, the sigmas, the weights. And so usually for the mu's, we would use a Gaussian. For the sigmas, we have flexibility over what we want to use, but often the inverse gamma distribution is a reasonable choice. And for the weights, we would use a Dirichlet distribution. And many choices that we might make for these priors would immediately rule out these sorts of pathological solutions. So let's suppose we had something like a log normal distribution for the sigmas. Then having like infinite would have zero measure under that distribution. And so we wouldn't find those types of solutions. But we can be, so that would apply even if we were just maximizing the posterior instead of doing full Bayesian inference. This would sort of create a regularizer that would remove those pathologies. The benefit of full Bayesian inference in this setting is you can then be even more relaxed about what priors you have. And quite often you'll still see very good results because you can then have priors that even include some of these crazy solutions as long as the posterior doesn't have like full probability for those solutions. So these would be kind of the standard choices for these priors. One could really choose a range of different things. These are often the choices because they lead to conjugate posteriors. So if we use these priors and then we combine it with a mixture of Gaussian likelihoods, we often get at least kind of conditional posteriors that have the same functional forms as these priors. And so everything stays to some extent analytic. Okay, so we've heard a little bit about a procedure called principal components analysis, which is used for doing dimensionality reduction. So we might, it's kind of well known that even though a lot of our observations in the real world are really, really high dimensional, they seem to mostly live in a low dimensional space. And this is actually what saves a lot of machine learning procedures. So I don't know if Kilian mentioned this at one point, but he has a really nice demonstration in his class of the cursive dimensionality for k-nearest neighbors, which is this very simple machine learning algorithm. If you're doing, say, classification, one way of trying to decide a class label for a test point is just to find the, say, k closest points and then do a majority vote of whatever the classes are for those points. And interestingly, for images and a lot of natural data that this algorithm is applied to, it really shouldn't work because in high dimensional spaces, if we assume that the data is, say, uniformly kind of drawn from some distribution, all of our points are almost the same distance from each other, and they all are kind of like on the boundary of this sort of this region where they've been generated. So if we imagine thinking about like a cube or something like that of equal lengths, and we're sort of sampling points uniformly in the cube, most of the mass of that distribution is going to be at the edges of the cube, because if we say increase the edges a little bit, we add a huge amount of volume. And so it seems like, based on these arguments, that a lot of these machine learning methods shouldn't really work at all. But the reason they actually work is because many of our data sets, even though they appear to be very high dimensional, actually live in some much lower dimensional space. So if we think about things like handwritten digits, even though maybe they might be like 100 by 100 pixels, so this sort of looks like a 10,000 dimensional data point, you could capture essentially everything you would ever want about that image using maybe like a 10-dimensional representation. And this starts to become intuitive if we think about things like police sketching or something like that. Like, let's say we're trying to find someone and someone's observed them and they're kind of recalling various features about that person. Probably after they've said about 10 to 20 things, a skilled portrait artist will be able to draw something that actually very much resembles that person. We wouldn't need to say 10,000 different things to get reasonably close. And so a lot of structure and data is captured in quite a low dimensional space. Let's just get to PCA. So the basic algorithm for PCA that you've probably been introduced to is you have some data matrix X. So it contains your data points. And I'm just trying to make sure I get the sort of standard notation right, because often there's sort of a standard convention people use for this. So often the data matrix is expressed as like an n by d matrix, where n is the number of data points we have and d is the dimensionality of each data point. So it's sort of like this. And this is d columns and rows. Sometimes people write it as d by n, and really we should be robust to whatever people do for this, but sometimes it can be confusing if we just flip it and you're assuming it's something else. Okay, so quite often what we do then is we just take X transpose X, which is referred to as kind of the empirical covariance matrix for the data, and it actually is rooted in maximum likelihood estimation of a Gaussian. So that's kind of the estimator essentially we get for the covariance matrix of that Gaussian if we assume those points have been drawn from a Gaussian. And then what we do is we take the eigendecomposition of this. So find this and then basically get the eigendecomposition of X transpose X, which I'll call C. And so we just do, CV equals VD, where V is a matrix and its columns are the eigenvectors of our empirical covariance C. And then once we have those, so let's say the entries, maybe I'll say U because it's a little bit, we'll just make everything orthonormal. And then once we have those eigenvectors, what we can do to kind of get into the low dimensional space is for any given data point xi, we just take the dot product of xi with whatever sort of eigenvector that we want to use for our principal components. So basically, if we're taking the first 5 principal components, we take the eigenvectors corresponding to the 5 largest eigenvalues, and then we would form xi transpose U1, U2, up to whatever, let's say UR, if we're taking the R principal components, and that gives us our R dimensional representation of the data. Okay, so that's PCA. And the standard derivation for PCA, there are really 2 derivations, but I would say the one that's most commonly used is this idea where we actually do these projections. Like we imagine there's some set of vectors that we're projecting our data with, xi transpose v1 up to v whatever vr. And then once we've projected those data points, we say, well, how do we choose v1 to vr to maximize the variance of that projection? And it turns out that the solution is using v1 to vr, which are just the eigenvectors of the empirical covariance matrix of the data. And this has sort of an interpretation of kind of like minimizing the distance basically between our original data points and their orthogonal projection onto some kind of plane. So that's kind of the vanilla kind of PCA derivation interpretation. It turns out that PCA is actually just a special case of density estimation. And I actually like this derivation much better than the original derivations, partly because I think it's easier to understand in a lot of ways. I mean, you could sort of rationalize why we want to maximize the variance of a projection and things like this. It seems to be retaining information and so on. But the probabilistic PCA approach is even like a little bit more intuitive, I think, and sort of easier to recall. So the idea is we start by forming an observation model, just as we do in supervised learning when we're doing regression or classification or whatever else. So we start with our observation model for our high dimensional data points. So we say that we've got X, it's D dimensional, D is large, And we're going to say that's equal to a projection, maybe I'll call it capital W, times Z, where Z is low dimensional, it's R by 1, and W is a D by R matrix. And then we add Gaussian noise. So basically, this equation is just a generative story for how we create our observations X. So we see the X's, and we're assuming here that the X's are actually equal to a linear projection, a matrix, times a very low dimensional vector Z, plus some kind of noise, which lives in the d-dimensional space. It kind of brings us back to X. So like the sort of assumption really at the core of this is that there's this like low dimensional Z that corresponds to every X. And even though Z, there isn't sort of an exact relationship between Z and X, the discrepancy that we get between the sort of projected X and the original X is due to just observation noise. And we just assume that that noise is Gaussian. So we put a distribution on Z, typically N0I, and we put a distribution on epsilon, which is N0 sigma squared I. And then it's really just back to the basics of maximum likelihood again. So we have our data set x1 up to xn. Just as like an incidental aside, often when people first learn about PCA, they start with the x's and then they go to the z's. Probabilistic PCA in equation 1 is kind of going in the other direction. It's sort of saying, let's start with the z's and then figure out how to create a story for how the x's are created from the z's. But really, it's identical. It's just kind of thinking about it from the other direction. And I actually like that perspective a little bit more too, because I mean, this is a notion that actually frequently surfaces in probabilistic modeling. We try to come up with some sort of causal generative mechanism for how our data are produced. And I feel like, you know, it's like the Feynman quote, like if you can't create it, you don't understand it kind of thing. Like I think thinking about how we can actually create our observations really helps us understand how we want to model them. And that's really what we're doing with probabilistic PCA. And so we've got our data set x1 up to xn. And given the specification in equation 1, we can write down our likelihood. So what is P of D given W and Z? And so that's just going to be a product from I equals 1 to n of P of xn given W, Z. Actually, we're going to get sigma squared there too. And this is really a lot like what we saw in regression when I said y equals fxw plus epsilon, and sometimes fxw could be something like w transpose x. Like mechanistically, this is almost identical. The only difference is we don't have labels, but it doesn't really factor into our procedure in any very significant way. And so we can look at equation 1 and say, well, if we're given z, and we're given W and we've got epsilon, then clearly X is also Gaussian distributed and its mean is going to be WZ and its covariance matrix is going to be sigma squared I. So that gives us this expression. So this is Gaussian in Xn and its mean is going to be WZ and its variance is sigma squared I. Okay, now we can also write down our likelihood not given Z. So we can use the sum and product rules of probability to just write down what is P of D given W and sigma squared. And this is a little bit harder to see, but it's still, you know, it's not too bad. So if we look at equation 1 and we say, oh, we're not given Z anymore. So Z is not deterministic, it's random. And we've specified the distribution for Z, it's just N0I. So what we get is a matrix times a random variable Z plus another random variable epsilon. Now, Z is Gaussian distributed. And so if you multiply Z by a matrix W, that's also going to be Gaussian distributed. And it's just going to have a modified covariance matrix. And then if we add two Gaussian distributions together, we're going to get a Gaussian distribution again. They're closed under addition. And so we can do the algebra, basically say, okay, well, by that reasoning, X again is going to be Gaussian distributed if Z is not given. In this case, it's random. And we just need to work out its mean and its covariance matrix. And that is going to be, so we'll just write down this likelihood, P of Xn given W sigma squared, and this is going to be a Gaussian in Xn, and its mean is going to be 0 in this case, and its covariance matrix is going to be W transpose plus sigma squared I. Okay, so we've got this. Next step, optimize P d given W sigma squared with respect to W sigma squared. So just maximum likelihood. And when we do that, we find that the columns of W are the eigenvectors of the empirical covariance matrix for the data. So that's an exact recovery of PCA. With one way of kind of writing PCA starting from the Z's is just to say we have this basis U1 to UR for our eigenvectors of our data covariance matrix, and then we just have a bunch like Z1 up to ZR that is sort of, that's sort of adding these things together. And so we can also, using the rules of probability, say, well, what is P of Z given X? And it turns out if we also condition on W hat ML, that's going to be a Gaussian, and its mean is equal to W transpose X. So we see that basically we get these eigenvectors and their inner products with X for any data point X is our mean. And then we get also like an expression here for a covariance matrix. So this is sort of a probabilistic rederivation of principal components analysis. So I guess, the next question is why is this better than the original derivation? So I think there are a number of reasons. One is it allows us to immediately unify dimensionality reduction with density estimation. We see that they're actually the same thing, even though they're talked about as kind of separate units in classes on unsupervised learning. Two, once we have this sort of model in equation 1 for our data, it's very easy to change it and get sort of different properties. So here we're recovering PCA, but what if we make some other assumption? Like what if epsilon isn't Gaussian? What if it's t-distributed or it's got some other property? We can now reason about that. What if we wanted to handle this in a Bayesian way? Like what if we wanted to have like a distribution over what dimensionality the data could have? Or we want to sort of have a distribution over W or sigma or some other parameters. We can now that we can write down a likelihood, we can easily write down a posterior if we specify a prior. And even more interestingly, what if we believe that the data actually does have an intrinsic dimensionality and we want to know what it is? This sort of allows us to do that in a really cool way. So there's something you can do where you can put a distribution over the parameters W and write down what is the probability of D just given R by integrating away P of D given W, which depends on R. PW, DW. And this expression here is actually a consistent estimator for the real dimensionality R of the data. So as we get more and more data points, this will actually collapse onto the true dimensionality of the data. And it respects something in Bayesian inference that we don't have a lot of time to talk about, but I think is quite interesting, where you get this sort of automatic Occam's razor behavior. So if we think about that generative model, if we use a really high intrinsic dimensionality, we're able to generate quite a large range of different data sets, but none of them have very much probability because this is a proper normalizable density. It can't give everything a lot of probability. Whereas if we use a small r, we're only able to generate a smaller range of data sets, but we give those data sets more probability. Now, that means that if we're considering a data set that could have been generated with the small r, even though both of these models are consistent with our observations, the one that is more constrained will automatically be favored by the Bayesian evidence. And so that sort of explains why we could use this as a mechanism for trying to find the intrinsic dimensionality. And nicely, it's actually consistent with the true dimensionality as we get more data. And it tends to work very well, even in cases where we have a very small number of data points. So that's just sort of an aside about probabilistic PCA. Finally, let's introduce another algorithm, k-means clustering, which again, we can actually see as a special case of density estimation. So what is k-means clustering? So let's say we have data, x1 up to xn. So these are n observations of d-dimensional variables x, like before. And our goal is to want to partition the data into k clusters. So what's a cluster? So intuitively, a cluster is a group of points whose distances are less than the distances for points outside the cluster. Now, it's a little bit hand-wavy because we have to define what distance means and so on, and what distance we want to use. And that will actually have an important effect on a number of different clustering procedures. And sometimes there's, there's a bit of a vicious circle, like it's sort of, whether something is in a cluster or not depends a lot on your representation of distance. And if you're working with high dimensional data, you might want a very non-Euclidean notion of distance, but let's not go into that yet. So let's introduce some notation. So let's let mu k be the center. Okay, I'm going to be really careful about notation. So there's like big K, which is the total number of clusters, and little k, which is an index. Let mu little k be the center of the kth cluster, and let r and k be a binary variable, which is 1 if xn is in cluster k and 0 otherwise. So sometimes we can say that, like if we're not using the little k index, we've got a vector r for every data point, and it uses what's called a 1 of k coding scheme, where all of its entries are 0, except for one entry, which is 1 at position k. Okay, so r n little k equals 1, r n j equals 0 for j not equal to k. So it's just a way of indexing our points. For every data point little n, we have this variable, and it says which cluster that data point is in. Okay. Now let's specify a loss function for trying to learn the values of r and k, the cluster assignments, and the means of the cluster. So what we do is we say, let's look at squared loss. So this says that, let's suppose we assign a data point to a cluster k, and that's very far from its so-called prototype center, mu k, then we'll incur a big loss. So we're going to try to encourage all of our data points to be very close to the cluster centers, or the cluster centers to be very close to all of the data points, rather. So this is the sum of squares of distances from point xn to its assigned mu k. So we want to learn, want to find r and k in mu k. So k-means clustering follows two steps. Step one, which we can call the E step, and we'll explain this in a minute, like why it's called the E step, is we choose initial values for mu k and minimize our loss with respect to Rnk, keeping mu k fixed. And then in step two, which is called the M step, we keep Rnk fixed and minimize L with respect to mu k. And then we repeat these steps until convergence using the latest values of these parameters. Okay, so if we consider step one, we can see that this equation for our loss, equation one, separates linearly across all of our data points n. So that allows us basically to consider each term separately. So we can sort of think of what we want to do for each individual data point, and that will be what we want to do for all of the data points. So if we just kind of forget about the outer sum and look at the inner sum, we can say, well, we want Rnk to be 1 for the distance that is smallest between xn and the current setting of mu k. And we'll make it 0 for all the other ones, because maybe some of these distances are really big and we want them to be 0 in that case for the indicator. And so that basically just means, in other words, assign data point xn to the cluster which has a prototype mu k, which is closest in Euclidean distance, in squared distance to xn. Okay, so that's pretty simple. So we basically just get R and k equals 1 if k equals argmin over j xn minus mu j squared, and 0 otherwise. And step 2, we fix Rnk, and then we basically just want to do very vanilla kind of optimization of this objective. So we have this sum of Rnk times Euclidean distance, which we can write out as xn minus mu k dot product xn minus mu k. And we can differentiate this with respect to mu k, and we get minus 2 n equals 1 to n Rnk xn minus mu k equals 0, setting this thing equal to 0. And then we get mu k equals sum n equals 1 to n Rnk xn over the sum n equals 1 to n Rnk. And so the numerator here are basically just represents all the points in cluster K, and the denominator represents the number of points in cluster K. So this solution is saying, take the mean of all of the points currently assigned to cluster K and let that be mu K. So that's pretty like intuitive. So this procedure first just says, well, assign each data point, like first sort of randomly initialize the mu Ks, assign each data point to the closest mu K, and then update the mu Ks by taking the mean of all the points assigned to each cluster. And so that's k-means. And that's really this update is why it's called means. K-means. We set mu k to the mean of the points assigned to cluster K. Okay, so we can actually see, and we don't have time to do the full derivation, but I think it's important that people are kind of aware of this connection and able to look it up. that we can rederive k-means as maximum likelihood density estimation with a mixture of Gaussians. And so if we assume that P of X equals alpha K n X mu K sigma K, and we estimate alpha K mu K sigma K using a special algorithm for maximum likelihood, using an algorithm called expectation maximization, maximum likelihood. Then you and you make a further assumption that epsilon k are just equal to the identity, or like a scaled identity, and they're all scaled in the same way, like say gamma I. Then we recover exactly the same algorithm for k-means clustering. And so this is kind of interesting in the sense that it also tells us that we might expect certain pathologies in k-means that could be alleviated by more expressive mixture modeling. So I'll give a quick example of that. We could suppose, for instance, that our data points are very correlated, such that they look like they are drawn from these sort of elliptical contours. And maybe we have two mixture components. Like, let's suppose this is like a mixture of two Gaussians with non-diagonal covariance matrices that we've used to estimate this distribution. And we can see, okay, this provides a very good generative mechanism for the data we observe. It could be that if we're doing something like k-means, that this point over here might actually be closer to this point over here than it is to the prototype of the cluster. And so then it might want to assign this point to a completely different cluster, even though for a real generative model, there's no way we would have been able to generate that data point using that other cluster. And so when we see that k-means is actually just a special case of Gaussian mixture density estimation, when we let the covariance matrices just be spherical identity covariance matrices, meaning that different points aren't actually correlated, we can also see partly why we might not want to use k-means, and how we can kind of generalize the k-means algorithm to account for correlations and so on. And a number of papers have been written about, basically modified k-means algorithms that try to leverage this insight that in fact k-means is yet just another example of density estimation, in the same way that PCA is an example of density estimation. And when we use that, we can build kind of more powerful methods. All right, thank you. That's everything for today's lecture. I had lots of fun talking in the summer school. I hope you enjoyed it, and feel free to reach out if you have any questions.
Well, thank you so much for really clear and very helpful lectures. I can see the lectures have been really popular. And I also want to applaud the students, both in the Zoom and also following through YouTube. It's great stamina, by now through the whole week, it's been very intense, but I sense that there's a lot of enthusiasm and people are excited to learn. So thank you so much, Andrew. And
I'd like to say thank you for organizing everything as well. I mean, it's a tremendous effort, and what we did was nothing compared to the effort you must have put into making this happen. So thank you.
It was work organizing, definitely, but it's actually it's really wonderful to watch my friends give such awesome lectures. I'm sitting here like, oh, they're so amazing. So it's been really nice. And when people try to make it accessible to students, it also becomes accessible to me. So I learn a lot. All right. So now we're going to switch over to the hands-on session TAs who have prepared the hands-on session notebooks. We have two lead TAs today, Sanae and Krishna. So Sanae is going to continue with the second part of the second notebook. That is the second part, focusing on probabilistic modeling and Bayesian approaches syncing with the topics that Andrew has discussed. Sanae, are you around? I saw you join, so you must be here. Can we, Jonathan, can you make Sanae a co-host so that she can share screen, please? Okay, thank you, Jonathan. Well, Sanae, now can you share your screen? Great, yes. Okay. Now, while Sanae gets ready, can we all send applause to Jonathan, who's the one who really worked really hard to do this very unusual, school using the platforms that we are all new to and made it all happen. I'm just really grateful. I think this really would not have been possible without Jonathan's hard work, dedication, and being very innovative. All right, so now Sanae, take us to the notebook today.
Yes, hi everyone. So today we're going to keep with the probabilistic modeling. We're going to start with PCA, dimensionality reduction, the topic that Andrew talked about today. Then we're going to move to Gaussian mixture models for an application of the EM algorithm in density estimation. And finally, we're going to see an example with K-means. I added a couple of lines of code just for you to be able to actually load the files from the Google Drive, because initially I was running this locally, then I realized we need these couple of lines of code. So feel free to just copy paste them or to download the notebook again. So first of all, we're going to talk about dimensionality reduction with PCA. And here's so the first thing. Let me keep executing as I go, just in case there is a problem with Thrive. So the data set that we're going to use is this data set, the MIT CVCL faces data set, and we're going to try to view those faces. So here you can see the kind of faces that we are interested in this PCA example. So the goal here would be that we identify the eigenvectors, a number of eigenvectors that would allow us to reconstruct these spaces without using all the information that we have. So here we want to use PCA for this task, and PCA aims to identify the best linear combination or the best linear transformation that we can use such that we view the directions with maximum variance. Now, the idea behind this, as Andrew explained, is that the directions that contain the maximum variance also contain the highest signal that we can learn from. So here, the principal components that best describe this construction are the eigenvectors of the covariance matrix. And we're going to extract them using this function from NumPy, linalg SVD. So it gives us an SVD decomposition components. And to visualize the eigenfaces, we're just going to retrieve k first columns that we also call that we also use to form what we call the eigenbasis of the face vectors. Here, as you can see from W, we only retrieve the first 100 here. And here we're going to see for each dimension what we are retrieving. And you can see that these eigenvectors, each one of them is extracting some important information or feature of the face. So for example, the first one seems to do more with the face. The fifth one seems to be doing more with like highlighting the nose. The seventh one is more concentrated around the mouth stage. And hopefully, if we can just choose these 100 dimensions, we can reconstruct the faces. So here we try to generate a new face, and we see that this is purely by inspection for now, but one can imagine how controlled generation can happen if you control for such facial features, which means that if you go back to these dimensions and you try to control for each feature you want to have, you can reconstruct things exactly the way you want. So here you can see that we chose 4 and 7 because those are the things that we care about reproducing in this new face or constructing in this new face. And then we're going to move to a very important like verification step, which is how much variance do those 100 out of 360 components explain in our data. So here we're simply going to take the sum of the corresponding explained variance, and we see that we are covering 70% of the variance, only taking less than 30% of the eigenfaces. And we move to density estimation. So we are going to consider the cloud function, and it looks like this. And here we're going to consider some samples to try to represent this this function again. So the big picture question that density estimation answers is, given samples from some underlying generative process, can we recover the process itself? And here we are moving to the supervised learning setting, from a supervised learning setting to an unsupervised learning setting, because we're trying to learn the density itself rather than trying to learn a relationship between X and Y. And as it turns out, we have already been doing density estimation using histograms. And you can see here that, okay, it's taking a while, but the smaller the number, the bigger the number of bins that you are selecting, the finer the distribution you can recover. So you can see that you get roughly the shape of the density here. Sorry. You get roughly the shape of the density here with 10, but you can move to finer things if you choose a bigger number of bins. So we're going to consider kernel density estimation. So in this case, we're considering the case of non-parametric density estimations, and we place smoothing kernels, which are defined here, centered at each sample, where the coverage is specified by a bandwidth parameter h, which is what we define here. And here h is given in the case of the Gaussian kernel, what it can represent. And in general, we'll write this way the estimated density, and this relates to the previous example as well. And a common choice is the Gaussian kernel, but you can imagine choosing other kernels for your density estimation. So here we're going to consider this. Okay, so you can see for the cloud function whether or not we're able to represent again this function using this Gaussian kernel. And this parameter h is representing a variance bias trade-off. So you can see that the bigger this parameter is, the more we're just getting a not very clear or exact form of the cloud function. So you would like to take a reasonably small or big parameter, but you can play around with it. And we move now to the Gaussian mixture models. So Gaussian mixture models are a class of discrete latent variable models, and we describe it while writing the following marginal density expression. So we introduce these latent variables, Z, that can give us an idea about the conditional probability of X with respect to the value that this latent variable takes. And the conditional probability here is considered to be a Gaussian probability. And the K's component in the mixture is a Gaussian component as well. And for a given set of samples, we aim to maximize the log likelihood using the density function. And this involves finding each mix. So this involves finding the marginal distribution for the latent variable. We consider the old faithful data set. You can also find the file in the Google Drive. And let me know if you find any problem loading the files from the Google Drive. And here, this is a reminder of the EM algorithm, the expectation maximization algorithm. So we solve a constrained optimization problem via the method of Lagrange multipliers, but it is not feasible to maximize this in closed form. But we can consider this this way to resolve it instead. So I don't know if you are if you need further explanation for the EM algorithm, but I can give that during the TA during my time on Gather Town. So feel free to tell me if you need that. So here we're gonna define a few functions: the GMM likelihood, the expectation, and the expectation step, and the maximization step. And we can visualize then the training of GMM. So you can see here the different steps. You can see that initially you have one density around a part of the data. We clearly, for this data set, aim to have 2 clusters of the data. So you can see that we slowly, each 5 or 10 iterations, we start to concentrate more around the different clusters, and we start to see the different clusters more clearly. So after only 20 iterations, we are already capable of seeing the different clusters for the data. And we can also alternatively, instead of defining these functions, we can just fit GMMs with scikit-learn using the Gaussian mixture package. And here you can see a similar representation for that package. And finally, we're going to finish with k-means clustering, which is another algorithm that uses the EM optimization algorithm. So we build the 2D synthetic data, and these functions basically just help us plot the data and plot the updates. So here is the data that we are considering. And we initialize the cluster centers, 4 of them, randomly, and we try to visualize how they are assigned through the optimization process. So here you see as the iteration goes, you can define the next iteration, and you can see, okay, I'm not getting the box where I can choose the number of iterations, because you usually set up the number of iterations, but I will try to fix this as we go together down. But usually you choose the number of iterations that you want to have, and you start seeing as you move in the iterations how the clusters are, how the centers are assigned. But here you can already see that we started with a random assignment of the cluster centers that are all around this cluster, but we ended up having cluster centers that actually do define our data set separately. So feel free to ask me questions during our time on GatherTown, and I will try to fix this step such that you can choose the number of iterations and visualize what happens then.
Great, thank you, Sanae. And next is Krishna. So the Gaussian mixture model was the core of tool that we developed for dealing with large volume data of X-ray diffraction data. And Krishna's notebook will cover how we use the Gaussian mixture model, and he's going to tell you about his notebook.
Hi. Yeah. So thank you for the introduction. And can you see my screen? Okay. Yeah. So so this is the X-ray temperature clustering, or XTEC, and you can read more details about this from the paper in arXiv. Like Una mentioned, the idea is to look at the temperature series of the X-ray diffraction data and see if we can identify phase transitions, star density waves, or things like that from the clustering of these temperature trajectories. And now here is a illustration of a simple situation where you have the intensity as a function of a parameter, and suppose you know this value is at 2 points, or in general n points, n is 2 in this figure. You can see that there are certain trajectories, and to find out what are the distinct trajectories, you can map this into a Gaussian mixture model problem. And from the clustering assignments of these Gaussian mixture model, from the clustering assignments, you can see that you have distinct trajectories with their corresponding mean and the variance. And that's the idea. And from these trajectories, if we can identify phases and phase transitions from the X-ray data, that's our goal. And this G can be any parameter. It doesn't have to be temperature, but here we use the temperature series to look at the physics. So it loads. So to run the code, it's like, again, you have to make a copy of this on your drive, and it loads the modules of extract modules from this GitHub repository. So you just have to run this this part, and that will load the GitHub repository. And yeah, you have to mount that on the Google Drive. So you just have to run that part. And to load the X-ray diffraction data. So here we have real X-ray diffraction data that was collected from at Argonne National Lab, Advanced Photon Source at Argonne National Lab. And it's the X-ray diffraction data of this compound, strontium, rhodium, tin, which shows a charge density wave phase below a critical temperature. And this would load the data from a Dropbox folder where the data is stored. And yeah, and this shows that the data has these many number of temperatures, and these number of H and number of K are the number of pixels in the H and the K reciprocal space. So you have 600 by 600 pixels, and these are the values of the momentum H and K, and this L is 0 in this case. So this is the dimension of, this is the HKL dimension of the data, that X-ray diffraction data that we have. And you can see what the data looks like. It has at 30 Kelvin, you can see that there are charge density waves at these 0.5, 0.5, and their equivalence in the Bragg peaks. But this charge density wave disappears at a higher temperature. So, and this is the peak that we are after. Like, can this algorithm detect the peak and identify the phase transition? At what temperature the phase transition happens? So here starts the expect analysis, which has two parts. The first part is pre-processing, which is like dimension reduction. So what we do is we find that most of the interesting features are kind of concentrated at these special points, and you don't need a lot of these background intensity, which we can remove. And the first step does that. And it also rescales the intensity so that we can focus on the efficient feature selection of the temperature trajectory. And the second part is the clustering, which is the Gaussian mixture model. And this also has two parts, the clustering and label smoothing, where, yeah, and we'll get to that soon. And you can play around a lot with this data. Remember, this is real data from a real object. So maybe there is some new physics that you can discover by playing around with the data. So yeah, so have fun with, so what you can do is like change the number of clusters or change the pre-processing and the clustering schemes and see what you can do. So this is the thresholding part, which removes the low intensity noise. And you can, yeah, so you can see what it does. It has this, so this is the density of intensities, and it kind of, it identifies the cutoff, which will select the interesting features that you see. And in the second, so that's the first step. And it also involves, and you can see that these are the intensities that pass the thresholding, which is a mess. And we want to find what is the nice order parameter from this large volume data, from volume intensity. Rescaling the intensity just removes the mean and kind of rescales it so that we can address this large dynamic range of intensities. And we can focus on just their temperature trajectories, the feature of temperature trajectory. Yeah, so after this rescaling, we have the clustering, the Gaussian mixture model clustering. The first part is just the usual Gaussian mixture model, where we can set the number of clusters here. You can change this value to 3, 4, 5, 2, 3, 4, 5 and see what happens. But typically what you observe is that once you cluster it, you can see that you are assigned a color for each cluster. You have 4 clusters colored red, blue, green, and violet. And these are the number of trajectories in each cluster. And if you plot them, you can see that the intensity trajectory, the rescaled intensity trajectory for each cluster has these properties, where the first one seems to look like the order parameter with some transition temperature somewhere around here, and you have some other trajectories. To see what these mean, you can look at their cluster assignments in the HKL space, and that's what this part does. And you see that in the momentum space, these pixels have these color codes. Or you can look at the zoom in part of it. You can see that there are these violet pixels, blue pixels, green, and so on. And now you can see that these violet pixels, which show up at these charge density wave peaks, they are the ones that have this order parameter like trajectory. Whereas if you look at the green pixel, which has this increasing in temperature trajectory, that's the diffuse scattering around the peaks. the Bragg peaks. Yeah. And we can do better by, we can remove these features that we don't want to look at for now and focus on the features that we want to look at. So let's remove the green and the blue trajectories. Let's see, green and the red trajectories, because the red trajectory is kind of nice at the center. So the second step clustering does that. You can remove the bad clusters. You can try experimenting with these clusters in case you want to focus on the Bragg peaks instead of, or in diffuse trajectories instead of the charge density peaks. You can play around with that. So you remove those clusters and cluster the remaining trajectories using the second step clustering. And you can see that after the second step clustering, you see a nice order parameter trajectory that shows a transition somewhere here. And if you look at the HKL assignments of those clusters, you can see that the charge density peaks are the ones that overwhelmingly have the order parameter trajectory. So now this XTech has identified where you have these, which peaks show the phase transition, what this phase transition means. But you can go, we can do better, because now we see that some pixels are kind of mixed. Like you expect these to be Bragg peaks, to be a single intensity, to be a single thing, but the clustering has identified different colors inside each peak. And that's because we have assumed that each pixel is independent IIDs, they're independent, but we know that that neighboring pixels are correlated, like they would be representing the same thing. And so that's what this part does. It's the label smoothing part, which kind of accounts for these correlations. So the label smoothing accounts for correlations not only in neighboring pixels in locally, but also between pixels that are related by a reciprocal lattice. So it's the kernel type is periodic, and you can see more details about how this smoothing is implemented in the paper or in the codes. Yeah. So and after label smoothing, if you run it again and if you do the clustering, you can see that you find this order parameter trajectory. And if you look at the pixel assignments, you see that the color assignments are kind of smooth over each peak. And the red pixel is the charge density wave peak, and that has this order parameter like trajectory. So yeah, so that's what so that's what this notebook shows, and you can play around with various things like the number of clusters, or instead of focusing on the charge density wave and the Bragg peaks, you can try what happens with the diffuse scattering peaks that we removed over here. And yeah, so those are the things you can play around with and see what you can find. So, and yeah, so feel free to ask questions during the classroom, or you can email me the questions if you find them later. So yeah.
All right, great. Thank you, Krishna. So the two notebooks from students in my group, Cole and postdoc Krishna, they involve data that was used for publication, and especially Krishna's notebook has real X-ray diffraction data that our colleagues at Argonne National Lab kindly made available to us. And those are like real raw data, and that was the promise of this school, that you get to put your hands on real data and see how we can use these tools to extract scientific insight from data. And so we all hope that this was useful. You find that that it helped you grow as a researcher. And although it's been a long week and you're probably all very zoomed out, our TAs still have energy, I think, it seems. So please meet with them at the GatherTown classroom and get their help in playing around with the notebooks that they worked very hard to make available for you. So I will meet you back in GatherTown. See you soon, everyone.